anatomical novelties, requiring many hundreds, even thousands, of adaptive changes in less than 2 million years, even less than 9 million years, perhaps even 50 million years. Dr. Meyer, I will think, but if you have any questions about that, I'm saying it doesn't add up. Yes, thank you.
I've got everything. 5 minutes. Okay. I'm going to make an additional point. The idea of population genetics was hatched in the 1920s and 30s before we knew about the information revolution in biology. And as a result of that, it made a number of assumptions that are still with us today and yet are not well founded. The main assumption it made was that it's easy to produce new traits by making with mutations. Genes were thought to be unitary entities prior to 1953. You change a gene, you automatically get a new trait. People didn't know how frequently they occurred, but it was assumed that it was easy to generate new traits by mutating genes. Since 1953, with the recognition that genes are actually sections of digital code along the DNA molecule, that assumption of population genetics has had to be revisited. And what it means is that as difficult as the problem is from the standpoint of neo-Darwinism and its mathematical expression in population genetics, the problem of generating new biological form, anatomical novelties, like all these cool structures that Rick was talking about in whales, is even more difficult. And in particular, what we recognize is that building new complex animals does indeed require lots of new information. Not complexity, as Dr. Prothero referred to it, but information, specified arrangements of sequences. If you think about mutating something, and you realize that you need information to build a new organism, just like you need new information to give your computer a new function. And you begin to think about it in light of the information revolution, it raises some other questions about the power of mutation. Ask yourself a question. If you've got a section of digital code, a section of alphabetic text, and you begin to randomly change it, blindly, are you more likely to degrade the meaning and function that's there, or are you more likely to enhance it? Clearly, you're overwhelmingly more likely to degrade it. And one of the reasons for that is it turns out that the ratio of the number of sequences of alphabetic characters that perform functions or are meaningful to the sequences that don't is very small. In a 10-letter sequence in the English language, there is one functional sequence for every 10 to the 14th, or 100 trillion non-functional sequences. So inevitably, you start to degrade things, you're going to move the sequence away from function into non-function. Now, this was intuitively, biologists thought the same thing in the 1960s about mathematicians, in particular mathematicians and physicists at MIT, who began to think about the plausibility, the mathematical plausibility of mutational theory. But they didn't know how, if the same thing was true of genes and proteins, that the ratio of the functional sequences were very small. The ratio of function to non-function was very small. And this question was taken up building on the work of an MIT scientist named Robert Sauer by Douglas Axe, who is the director of the laboratory at the Biologic Institute, which is where much of the laboratory research that Dr. Prothero says is not done is done. Axe began his research at Cambridge University, and he asked a critical question. The question was this: how rare or common are the functional sequences of genes or proteins in relation to all the possible ways there are of arranging the base characters in the genetic message or the amino acids in the proteins? If it turned out that the sequences were very common, that functional sequences were common, it was possible to imagine that by mutation you could kind of skip from one island of function to the next very readily. But if it turned out that the ratio of functional to non-functional sequences was astronomically small, then what you would have is a situation where mutation would be searching indefinitely, trying to find the functional sequences and not having enough time to do it, like looking for a tiny, tiny pin in a gigantic haystack. Well, Axe, through this period of 14-year research published in the Journal of Molecular Biology, determined that the ratio of functional proteins to the corresponding space of all the possible ways there are of arranging amino acids of that given length is astronomically small. The ratio is 1 in 10 to the 77th power. So to get a handle on that, imagine this. Imagine that you're trying to find the combination on a combination lock. But instead of having a combination lock that's just got 4 dials, or 10 as my artist has rendered, imagine you have one that has 77 dials with 10 settings on each one, and you have only one functional combination. Is it going to take you a little bit of time or a lot of time to search that space of all those possibilities to generate the new combination or information you need to unlock the lock? Obviously, it's going to take you an immense amount of time. And that is the measure the measure of the probability of generating one protein fold, a domain of a protein, not even the whole protein, okay, in axis research. Now, to build a new Cambrian animal, to build a lens-focusing eye, a compound lens-focusing eye in a trilobite, you're going to need many genes. To build the whole animal, you're going to need many genes. Arthropods have about 50 cell types, each of which have many dedicated proteins, many of which would not have been present in the immediate ancestor to the arthropods in the arthropod prior to that critical explosion that I talked about in my opening remarks. Now, one more problem as far as the generation of information. It turns out that you don't only need information to build genes and proteins. It turns out to build body plans, you need higher levels of information, higher order assembly instructions. DNA codes for the building of proteins, but proteins must be arranged into distinctive circuitry to form distinctive cell types. Cell types have to be arranged into tissues. Tissues have to be arranged into organs. Organs and tissues must be specifically arranged to generate whole new body plans, distinctive arrangements of those body parts. We now know that DNA alone is not responsible for those higher orders of organization. DNA codes for proteins. But by itself, it does not ensure that proteins, cell types, tissues, organs will all be arranged into body plans. And what that means is that the body plan morphogenesis, as it's called, depends upon information that is not encoded in DNA, which means you can mutate DNA indefinitely. 80 million years, 100 million years, till the cows come home, and it doesn't matter. Because in the best case, you're just going to find a new protein someplace out there in that vast combinatorial sequence space. You're not, by mutating DNA alone, going to generate the higher order structures that are necessary to building a body plan. So what we can conclude from that is that the neo-Darwinian mechanism is grossly inadequate to explain the origin of the information we need to build new genes and proteins, and it's also grossly inadequate to explain the origin of novel biological form, which is to say, it's not adequate. Thank you.
Thank you to all our debaters for staying within time. It was very impressive. I'm now going to call upon the affirmative to rebut some of the things that were said here, and you can rebut the rebuttal if you wish. This is an opportunity for us to really engage in debate. I'm going to encourage everybody now to fill out your questions and hand them to the ushers. And the usher should bring them up to me.
Okay, let's see if the microphone's working here. Yes? Okay, good. All right, Stephen, you started off by accusing us of not addressing the question on the table, which is, has evolutionary theory adequately explained the origins of life? Your side didn't even mention the origins of life. So you just wasted your 25 minutes if you want to stick to the technical reading of the question on the table. And in fact, we did. Of course, I just blasted through in 7 minutes, and Dr Prothero gave you a 15-week course in 15 minutes. He did 1 minute per week, and he gave you the origins of life and the origins of what you were concerned with, Stephen, novel biological forms, and showed you how you can even get information increase in mud by your definitions. So we, in fact, did address this quite clearly. My second point is that Dr. Sternberg made a point about the difference between the history of change within a lineage and then the causes of the changes.